For example 6, find the intervals over which f is differentiable. So remember, this word differentiable simply means that you can take a derivative at a particular point. The derivative exists there. So on number 1, we've got an absolute value graph. Number 2, we've got some sort of rational function. And recall that derivatives fail to exist under three possible conditions. Maybe you have yourself a sharp turn, maybe you have a discontinuity, or maybe you have yourself a vertical tangent line there. So on number 1 with the absolute value graph, we know there's got to be a sharp turn someplace. So that's where the derivative is going to fail to exist. So where the heck is this sharp turn? Well, I can think of this x minus 5 as being translated 5 units to the right, or I can just take what's in the absolute value brackets, x minus 5. It's like finding the x-intercept here. Set it equal to 0. Add the 5 over x is equal to 5. That's where that sharp turn is going to be. So the derivative is going to fail to exist here due to a sharp turn. Yeah? All right. So we want intervals over which this is differentiable, and it's everywhere except 5. Negative infinity to 5, or union, and then 5 to infinity. Let's compare that to the domain, shall we? So the domain, well, I can take the absolute value of anything that I want to. If I think of the graph, there's no gaps, there's no holes, and there's vertical asymptotes. This is all real numbers. This one's from negative infinity to positive infinity. So if we compare these two sets here, where it's differentiable and its domain, you can see that we left out a point on the where it's differentiable. At the very beginning of this lesson, when we're talking about the domain for a derivative graph, I said that it's always a subset of the domain because there are certain points in the original domain where the derivative may not exist. Where can that happen? Well, on this one, it was a sharp turn. If we look at number 2 is a rational function. So rational functions, we have the possibility of having, say, a vertical tangent. No, not a vertical tangent. What are those things called? Vertical asymptote. Or, holes. And those can happen where we divide by 0. So if I take that x squared minus 1 and set it equal to 0, x squared is equal to 1, x is equal to plus or minus 1. And these are vertical asymptotes, but how do I know they're asymptotes and not, let's say, a hole, point of discontinuity? Not that it matters, because either one, the derivative is going to fail to exist. But I know that because if I were to stick in either a plus or minus 1 into the top there, I would have a 1, and then on the bottom it would always be 0, which means it's going to plus or minus infinity, right? That's how we interpret that. Okay, so where does the derivative exist here? Oh yeah, let me point this out. This is discontinuity. Okay, so where does the derivative exist? Where's it differentiable? It is everywhere except plus or minus 1. So negative infinity to negative 1, in between negative 1 and 1, and then finally from 1 to infinity. What about the domain? Just to compare it. Well, the domain, if I think in terms of continuity, there's no holes. We just found the two vertical asymptotes, and there's no oscillation, so it's just exactly the same. So same. All right, so that'll pretty much wrap it up as some examples of looking at particular functions and finding out where that function is differentiable.